Hi everyone. I think we'll start now with the seminar. So welcome to the second seminar of the academic series. In order to get those 10 automatic PEP hours, make sure to attend the next two seminars, complete the feedback form after the last seminar, and fill out the sign-up form if you haven't already. It would be great if you could turn on your cameras as well. Today we are joined by Dr. Benjy Marks, who will give a presentation on how to surf an avalanche. He has been with the University of Sydney for 14 years. During his time, he has completed a Bachelor of Science, a Bachelor of Engineering, a PhD in geomechanics, and currently teaches multiple subjects. Apart from his time in USyd, he has also been involved with the ETH Zurich, University College London, and the University of Oslo, and the Swansea University. He also co-runs the Immersive Learning Laboratory with Jacqueline Thomas and is an editor of the journal Open Geomechanics, and is a secretary of the Australian Association for Granular Media. I'm sure you're all very intrigued to find out how to surf an avalanche, so I'll hand it to Benjy.
Thank you, Sangeeta. Share screen. All right, how's that?
It's good. You can see your screen.
All right, yeah, so hi everyone. Thanks for inviting me to give a presentation. Many of you may know me from a couple of classes that I teach. So some of you may have had me last semester or last year in environmental engineering, or maybe if you're lucky enough this semester in interdisciplinary engineering. Neither of those have anything to do with my research. And today I'm going to give you guys a bit of an intro into what I do and what we do in our research group. So I've got here on the title slide, that's me, the first person, Benjy, and then Zvonimir and Aranga, two of my PhD students. Zvonimir recently graduated, so he's Dr. Marinich now. And you may have had one or both of them as your tutors in the last couple of years. They tutored quite a few courses. Francois, James and Ita are all staff here, and we work together in kind of a bigger research group. We work in the particles and grains laboratory, where we do the kind of research that I'm going to be talking about today. And in particular, we're going to talk about how to surf a snow avalanche. It's not something many people have tried, but it's hopefully something you guys find interesting. So let's see how we go. So this is kind of the idea here. So this is a film of a free skier a few years ago. So he's wearing this backpack. I don't know if you could see, it's written ABS on the backpack. And that ABS is a specialty safety device produced by a company. They're not someone we work with. And so he's skiing here, and you can see a nice big slab avalanche forming as the snow moves underneath him. Everything looks all right at the moment. The flow is not too deep. It's about a ½ meter thick slab avalanche that's sliding. But then as this thing starts to deform a bit and passes over a cliff, it gets a lot thicker. So now you can see the same video, but from his head cam footage. You can see him disappear under the snow. One of the main issues here is getting buried in the snow in a snow avalanche. And so if you can find a way to not get buried, you have a much better chance of surviving a snow avalanche. So typically the two ways you die, one would be from being buried and suffocating. The other way is from hitting a tree. So here we're going to talk a bit about ways to not get stuck inside the avalanche. And you can see when they go to rescue him, he's got these airbags that are deployed behind him. This is that ABS product. So that's a thing you rip on the cord, and two airbags inflate behind you. And for some mysterious reason, you don't get caught inside the snow avalanche. So we got another video here from the same company, so this time with a snowboarder. And again, so it starts off small, then it accumulates into a small channel, and the flow depth increases, and you can see this moving quite quickly. and he's staying up on the surface the whole time. And that's really what you want to see. That's your best case scenario for getting stuck in a snow avalanche. Now, so the idea here is when you're wearing this bag, you for some reason stay on the top without getting buried underneath. So we don't just do research on snow, we do research on all kinds of things. This is a flowing mass in China from a couple of years ago, where actually some people did die in this landslide. And you can see here we've got a flow where we've got a huge range of things inside the flow. It's a lot of soil, also trees, cars. The range of sizes of the things in this flow from the car, which is a couple of meters long, all the way down to sand, all the way down to silt, which is just fractions of a millimeter. So a huge range of different things, all occupying the same space. And then one more here. So this is from 2019 in Brazil. It's quite a famous tailings dam collapse. This is the Brumadinho tailings dam. It looks pretty small until you start to realize the scales. That's a whole forest that's being demolished in seconds. There's another view of that coming up in a sec. And you can see this thing's moving fast, right? This is moving about the same speed a car moves, 30, 50, 100 Ks an hour in different parts of it. And heights up to 10, 15 meters. This is just demolishing everything in its path. In this case, especially, this is a huge issue because this is all very toxic material that's spreading into rivers and ecosystems outside of this mine. So these are some of the problems that we look at in the research group. I want to talk a little bit about the physics of what's going on inside of these. And at the end, we'll try to bring it back together to how to survive one of these flows. And we're not going to do any maths. We've only got 45 minutes, so we'll leave the maths for another time. And we want to talk about how to look at this in the simplest way possible. So on the left here, we've got a little landslide that happened. And we've gone in and I've manually colored all of the large rocks blue and the medium-sized rocks pink. And we left all the small rocks yellow. And we're going to use that color scheme for the rest of the presentation. So just remember all the big ones are blue. That's the idea. And so we want to represent this in kind of a simple way. And there's two simple-ish ways we can do that. The one on the top right, that's what we typically refer to as a discrete element method simulation. So we actually represent every individual particle in the flow, either as a sphere or some kind of shape. We let them hit each other, bounce off, and we simulate directly the whole flow. For a smallish system with millions of particles, that's kind of a feasible thing to do. For a large system with many, many more particles, that becomes less and less feasible to do very, very quickly. And then we want a kind of a different way to simplify this system. So the other one we're going to talk about is something that's unique to what we do here at Sydney Uni. And it's a different way of looking at the world. And it's the one in the bottom right, this little grid of cells. And each cell represents some particles where the color represents the size. So the way it works is we might want to represent this column of soil on the right. We split up the column of soil into little, what are called representative volume elements, little lumps of soil, like a very small box. And that small box has a grain size distribution. And so what we do is we actually take that box and we unwrap that into a long list, which we call the microstructural coordinate. And so every little cell here represents the same mass of grains of different size. So if you were to look across this whole row, you'd be able to get back the grain size distribution of this box. And so over here on the left, what we have now is a really simple representation of quite a complicated system. And we'll see how far we can get in terms of understanding the mechanics of what's going on. So the first thing we want to talk about that's happening in these flows is something called segregation. And segregation is this thing that we've represented at the top, where you start off with a flow which has got large and small particles mixed together. And as they flow down the hill, they're colliding with each other and bouncing off. And we've got new void spaces opening up all the time. And as a void space opens up, other particles want to fall into it. And it's more likely that a small particle will fit in than a big particle. And we end up with all the small particles filtering down through the material and all the large particles rising up to the top. That's what you can see kind of schematically drawn here. And it's something we see a lot in these flows. They really control the behavior of the flows. So in terms of the simple cellular system we were talking about before, we could start off with some set of cells where we've got a mix of large and small particles. And then over time, we want to end up with all the blue ones at the top and the yellow ones at the bottom. And so what we do is we just say, if there's a yellow one on top of a blue one, they've got some probability of swapping. And so first of all, these two swap and these two swap. So we get these blue ones moving up, and then these two swap, and then these two swap. And by the end, we've ended up with complete segregation. So with a few more cells here, so we're still looking at height and time. We can see how this thing operates. We start off with a mix of cells, and then we keep swapping them all, and we end up with all the blue ones in the top right and the yellow ones at the bottom right. And this is fully segregated. We can zoom out a bit more, and we've got the same picture up here on the left, but now it's with many, many, many cells. And we can do the same thing. So this is just, we've run the simulation once. We can run the simulation twice and average the two. And so we're looking at the average size everywhere. So pink would mean in one simulation we had yellow, and in the other simulation we had a blue. So sometimes it's pink, sometimes it's blue, sometimes it's yellow in this patch. But by the time we get to the end, it's all segregated. So now if we just, instead of averaging 2, we average 20 or 200 times. In the bottom right, we've got this system here, and it's nice. It's a solid pink triangle, and then it goes into blue at the top and yellow at the bottom. And this is now starting to really represent what's happening in the system, where we can actually see that it's nice, uniformly mixed at the beginning, and then it segregates over time as we get to the end. And we can do the same. So we have this segregation mechanism that's going on, but we don't normally see perfect segregation. We also get a lot of mixing going on. And we can represent mixing in a really similar way. So anyone who did environmental engineering will remember that we solved the diffusion equation. We did that stochastically, and we did it with the exact model I'm talking about here. So we have stuff in one cell, and with diffusion, with stuff mixing, it's not just as we had before with segregation with things swapping vertically. Now they move randomly, either up or down. And so we can start off with a system that's perfectly segregated, and we just have them randomly swapping up and down. And over time, after all these swapping operations, everything will be nicely uniformly mixed as we get to the end. And we can do the same thing. We can run this simulation once or twice or 20 times or 200 times. And after 200 times, we've actually got a numerical solver to solve the diffusion equation just by doing this small swapping operations. And these gray lines, which are drawn over the top, they're actually the solution to the diffusion equation. You can see we're actually getting, we're actually getting a reasonable solution to the underlying equations here. And the last really important thing that's going on in a snow avalanche, so we talked about segregation, where all the large particles go to the top and the small ones go to the bottom. We talked about mixing, where all the particles are turbulently mixing over time. And the last important one is crushing. So that's particles breaking in half and turning into smaller particles. And this one's a little bit more complicated. So we've got a couple of situations here. One is that we've just got a few large particles and lots of small particles. And you can see here when we're in this kind of situation, these large particles, they've actually got a lot of small particles touching them. And so when you apply a lot of stress here, we've got lots of little forces all being applied all the way around this large particle. And it's actually quite snug there. So it's quite hard to crack it in half when it's being squeezed concentrically from all the directions. But there's the small particles here, sorry, they've only got a few neighbors. And so they're getting loaded either diagonally or with 3 points, and they're quite likely to crush. So in this situation, we expect all the these red ones to turn into even smaller orange ones. And the opposite's kind of true when we have lots of large particles and just a few small ones. Here, the small particles are just kind of floating around, and it seems like the large ones are carrying all of the load. So in this situation, we probably expect all the large ones to crush. So we've got a mechanism where really particles that are close to the average size are more likely to crush. And so that's half of the story. The other half of the story is that small particles, just by their very nature, are stronger. So you could imagine that you start off with a large rock, it's got cracks everywhere, and you carve out a nice large particle and it's still got the cracks in it. You carve out a small particle and it's still got the cracks in it. But because it's smaller, it's got less cracks in it. And so the net result is that this small one ends up being stronger than the large one. And so with these two mechanisms, we can decide which particle is going to crush for any given applied load. So we can look here, this is what's called uniaxial compression. We can take a cup, fill it with soil, and load from the top, and we're just going to crush these particles as we load them. And so at the top is an experiment, and the bottom is the bit, how this crushing model works. And so the x-axis on all these graphs is the grain size distribution. So on the right is the largest particle, and the left is the smallest particle. It's 1,000th of the size. And the y-axis is the cumulative grain size distribution, or the percentage finer from soil mechanics. So when you start in the top right, that means that all the particles are smaller than this size. And we run this thing for 3 different types of soil. So one would be monodisperse, where all of the particles are originally between a size of 1 and a size of 1/2. They're all pretty much the same size. A bidisperse, where half of them are a certain size, or but 60% of them are one size and 40% of the other size. Or a polydisperse, where we have a huge range of sizes. And as we increase the normal stress, these things start to crush and we start to produce finer and finer particles. And you can see here this model, so that we have the experiment at the top, we're crushing a carbonate sand, and the model at the bottom. The model works quite nicely, where we reproduce this long tail of fine particles being produced. So we can do more than just crushing. So here, this is what's called a ring shear. For those of you who've been to the soils lab, you may have noticed the giant ring shear in one of the rooms. So this thing, we do the same thing. We apply this load from the top. We've now got a soil in this concentric ring. And after we apply the load from the top, we're going to start twisting that ring over time. And so we're going to be both giving it normal stress and also shearing that over time. And what that shearing is going to do is that's going to start mixing up the particles. So we're going to have both crushing and mixing going on. And so when you have crushing and mixing, we actually end up with very different sizes in the material. We get lots more crushing happening as these particles are. So the particles originally we crush until there's one large particle surrounded by lots of small particles. But then as we start to shear, we mix them up again and the large particles find each other and then they start to crush. And so these kind of simple models now capture this behavior quite nicely. So an avalanche really, to me, is something that looks a bit like this. We start up with a certain material at the top of the hill, we throw it down the hill. By the time it gets to the bottom, we've produced new finer particles, those orange ones, and we've also sorted the system. So we typically end up with what's called a bulbous head. So we get all these large boulders at the front of the landslide or avalanche. And then we end up with this tail of fine particles out the back and this complicated structure of different sizes in different places. And what we can do with this simple model is we can run all these things at the same time. We can turn on segregation, mixing, crushing, and we can see what happens. And what happens here is that we start off at the beginning with all large particles. And then, so these are 3 different amounts of mixing going on. But the important thing is here that as we're running it over time, we're generating these fine particles at the bottom. The large particles are segregating to the top. And we've got 3 sampling points here, the red, the green, and the brown, and they correspond to this red, green, and brown lines. And these are those cumulative grain size distributions from before. And we actually get these nice, what are called log normal grain size distributions. This is something that we see in reality in snow avalanches and in landslides. All right. So that's kind of the summary of this like basic little toy model to try to get your heads around the physics that's going on. But we can do much more. And one of the things that we do here is we try to develop new numerical tools to solve these kinds of equations. So you might be familiar with the finite element method. So we develop new methods similar to that. This is the polydisperse material point method for those keeping track. And this is a method specifically to try to model the things we've just been talking about. So we start off with some lump of material, which is the black parallelogram. And that's the continuous lump of something we're trying to represent. We turn that lump into a bunch of points, and each point represents a little lump of mass, and each of those points has a grain size distribution, which I've represented with this little wheel here. And then what we do is we take these lumps and we project them onto a mesh. So we end up with these points on the mesh. They've each got different amounts of mass and grain size distributions. We do all our calculations on the mesh. We solve all these equations that are related to the physics we talked about before. And we work out where are the large particles going? Where are the small particles going? What new sizes are evolving? and then we map them back onto these material points and we let them evolve. And so we do this thing in a loop and we iterate over and over again, and we can actually track the evolution of this kind of material over time. So that looks a bit like this. So here we've got the same grain. So this is the whole world's tilted at 30 degrees. And this is what's called a dam break problem. So we imagine we've got a box of material with a wall holding it up, and then we just remove the wall and this whole thing collapses. And so this thing here now is the run out of a avalanche. And the only difference between these three is the initial way we've sorted the grain. So it's the same grain size distribution overall, but in the top one, we've got all the large ones at the top and the small ones at the bottom. At the bottom, it's the opposite with the small ones at the top. And in the middle one, they're uniformly mixed everywhere. And as you can see, they behave quite differently, actually. We have the one at the bottom running out further and faster, and we can see this segregation and crushing dynamically happening over time. So we now have these kind of systems where we can really predict for a given avalanche where it might run out to, how fast it might be going. If you were to design a slope and you were going to do that in layers, what might be your worst case scenario for your layering? We can also do all kinds of other things. There's the simulation of, well, this is a square drum that's rotating with material moving around. We can do all kinds of industrial operations like this. All right, but so we have all these fancy simulations, and the question is, how the hell do we know if they represent reality? All we have is those videos of skiers getting caught in snow avalanches. And we need to get much better experimental data to be able to try to validate these models. And so many of you may not be aware, but we actually run an X-ray lab in the basement of the civil building. So people like myself, we develop new CT scanning algorithms to do CT scanning and other types of X-ray methods to understand what's going on inside these kinds of flows. And so here I'm actually presenting the PhD work of Mara Zvonimir Marinic. Many of you may know him. So this is the kind of experiment he was running. So we've got a bunch of glass beads in a jar, and the bottom of the jar, we're vibrating on a vibrating stage. And you can see all the grains inside jiggling and moving around. And one of the things we wanted to know is how much are they jiggling? So we have this idea that this jiggling is really strongly controlling the behavior of the material, but we don't have a good way of measuring it. So what Mara did is we took our X-ray system. So here in the bottom right, we have an X-ray source. It's like a light bulb, and it's light shining out blue light here, which are the X-rays. And then they get caught on a detector panel in the top left. And that detector panel is like the camera. And we can see everything between the source and that detector panel. And so we're seeing here a projection of all of the grains onto that detector panel. And you can see there's three kind of dark dots. That's 3 steel balls buried inside there somewhere. So with this X-ray source and a second X-ray source, we get 2 different views of those same balls. And what we want to know is where they are. So with a method called triangulation, we can say we know the 3D geometry here. We can pass some imaginary rays through these particles. And if we believe everything is working well, we should be able to track these grains over time. So these are the kinds of videos we can record with this. So these are called radiographs. It's not a photograph, it's a radiograph because we're doing radiography. We're actually passing the rays all the way through the material. And you can see these 3 balls moving around over time. And so what we can do here is we can track those balls. So here's the trajectory of one of those balls over time. You can see, so the blue cylinder is the whole experiment, and the ball starts off at the black end and slowly moves towards the white end. And it's doing this dance as it goes around the edge of the container. So what we have here is that all the flow is going up. So if we have the cylinder here, all the flow is going up in the middle, across at the top, and back down at the edges. And this particle is getting trapped in that. And what we're also seeing is that we have this primary flow going this way. We also have a very slow flow going around circumferentially as well. And so by tracking this particle over time, we can build up images like this. So this is the average velocity field everywhere as we slowly let this thing work its way through space. So the left-hand side here, that's actually the center of the axis of symmetry of the cylinder. Along here is the bottom of the cylinder, the exterior wall, and this is the free surface here where the grains are just free to move. And so we can see these grains moving up here in the middle of the container, rolling back down, and then getting caught down on the right-hand side, and they're actually getting stuck in what's called a convection roll. We're getting this slow convection inside the system just due to the vibration. We can do a bit more than that. We can actually get a map of what's called the granular temperature. So again, for those of you who remember anything about environmental engineering, you know that we were very concerned about the temperature and definitions of temperature. So the temperature is a measure of the kinetic energy of molecules in the air. This granular temperature would be a measure of the vibration of these grains. So not in degrees Celsius. Here it's measured in the actual velocity of the grains. And you can see these things are bouncing around at the surface, bouncing around a little bit due to the impact of the vibration stage at the bottom, and then also in a region near the wall. And we have, I'm not going to talk about them here, but we have quite complicated mathematical models to try to relate these kinds of measurements to the behavior of these kinds of materials. All right, so that's seeing one particle and tracking it as it moves around in time. But we can do better than that. If we want to be able to see everything, and I mean everything. So we've done lots of other kinds of tests. What we do in these ones is the same idea. We have two X-ray sources, two X-ray detector panels. And this time we've got a rectangular box, and it's got a long strip hole at the bottom. And all these particles are flowing out through that hole. And from the two different directions, we get two different views. So these are two experiments, both happening in the box, both looking down the axis where the flow is coming out. So this is the outlet here of the glass. On the left is with glass beads, outlet on the right here with rice. Let's just go back to the start. So I don't know if you can see at your end the texture here. You can kind of make out little glass beads here, and over here on the right, I really see this texture from this rice. And with my eyes, at least, I can see that aligning as it comes out through the outlet at the bottom. And so one of the things we've spent quite a lot of time on is try to analyze in detail what's happening inside these videos. So this is a video of the glass beads, and now it's got lots of little white arrows everywhere. And these white arrows, we have a technique now where we can try to measure the velocity field everywhere inside this material. And you can see it's coming out towards the outlet. We did the same with lentils. So here you can see we actually get these big dead zones with the lentils. And this flow just coming through the middle. And if you own a lentil factory and you're interested in storing and dumping out your lentils, this is the last thing you'd ever want. You've got lentils here from 10 years ago, slowly rotting, and you keep putting new lentils in the top and they come out and you're slowly getting rotting lentils coming out into your nice clean supply. We do the same with rice. Here, even the system's actually quite unstable. So here it's flowing up towards the top right corner and then waves around a little bit. And again, we get this, what's called rat holing. You get this rat hole of material coming down. So that's really nice. We can actually see the velocity fields inside. We can do more than just see the velocity fields. We can actually see for these rice and the lentils where they have a specific shape. We can try to really see and get a measure of the shape here. And so what we do is we take our images over here, we cut them up into little patches of image, and we take a 2D Fourier transform. So Fourier transform will turn this thing into different modes or different frequencies. And so we're looking at frequencies inside an image. So they're really things of different size, where we're looking for actual wavelengths in numbers of pixels. How big are things in the image? And we can look at waves going up, down, waves side to side, waves diagonally. And so what we're really looking at here is, are there things in this image that are oriented or aligned or have the same size? And with a bit of maths and some tensors, we can start to represent what's going on inside this system. So we get a tensor for this image, like the same way we have stress. We get 4 numbers for it because it's a 2D patch. We take its eigenvalues, that'll give us the principal things in this tensor, the same way we have principal stress. And we're going to represent them as an ellipse. So if the two principal things are the same, the ellipse will be a circle and there'll be no alignment of the particles. If it's very aligned and we have one principal thing much bigger than the other one, we'll see the alignment of the particles and we'll know their direction. So here at the top is rice and the bottom is lentils. And these are the same videos we just showed with two different opening widths at the bottom. And here you can see at the top, very weak alignment. And then as they come down towards the bottom, we're actually getting a quantitative measurement now of the angle and the magnitude of that orientation as these things start to align. And obviously the mechanical behavior of the system is really tied to the alignment of these particles. And the white lines over here, there are measurements of the velocity field. And we can see that there's actually a small misalignment. So the particles do come generally towards the same direction as the velocity field, but not quite. There's always an offset there, which is something we're working on understanding. We can do more with the same ideas. So with this tensor analysis, we were getting the alignment of these particles. We can also use the same kind of ideas to calculate the typical size of the particles here. So we're looking for wavelength. We want a really strong wavelength in all directions. That'll tell us that it has the same size in all directions. So what we actually do is we take radial averages here at different radii, and we can construct this image of the energy versus radius. And when we do that here, you can see we get some clear peaks. For 1 and 3 mil glass beads, we get clear peaks at 1 mil and 3 mils. For the rice and the lentils, which have more than one, so the rice has 1 long axis, 2 short axes, lentils has 1 short axis, 2 long axes. So they don't actually have a well-defined size. They've got a couple of sizes. And so we get much big, blurrier, wider peaks here, but we still pick up their principal orientation, principal size. So we have now a method to get the size, the alignment, if there's any alignment, and the velocity field as things are flowing through the system. So now we're really getting close enough to be able to come back to our previous things. So we're really interested in segregation, when we have a mix of sizes that's split apart, mixing where these sizes mix together, and crushing where we're actually generating new sizes. And so this is an experiment we've run in our X-ray lab. This is not the X-ray, this is just a normal video. There's a conveyor belt at the bottom. There's 3 different sets of particles there. The small white ones, medium-sized green ones, and large red ones. And as you can see over time, we're getting all the white ones down one end and all the red ones down the other end. At least that's what it looks like from the outside. We have no idea what's happening inside. And the game here is we want to know really where are all these different sizes and how do they evolve over time. And so this is what the X-ray looks like. So here you can see, so we have the conveyor belt moving left to right along the bottom of the image. We've got a wall on the right-hand side. So as these particles are slammed into the wall, they get forced up and around. And these white arrows are our measurement of the velocity field. And so now we can't make out individual grains, there's too many of them, but we can see fluctuations in the material. And so here, when there's small particles, we'd expect small fluctuations, and large particles, we expect larger ones. And so we can use these Fourier transform techniques now to go in and be able to try to identify what sizes do we have there. And in this case, if we look just for the concentration of those big red particles, we see almost none of them up near the wall. There's also a little core of none of them down here. And we get this ring of quite a lot of red particles that you can't see from the surface buried inside the material. And so for us, when we're trying to make models and build our understanding of how these things work, if we don't have these kind of X-ray techniques or abilities to see inside the material, all we can see is what's happening at the edges. And that's not really representative of what's happening inside. And so it's led to a lot of confusion, and we haven't made a huge amount of progress in this field in the last 50 years, mostly because we haven't had this fantastic experimental evidence that we have now. So this is a PhD work of Aranga Delangeli, another one of my PhD students. You may have had her as a tutor. And she's looking at how these, so we have a flow moving over a bed, maybe of snow. How does that bed erode the existing snow as it comes over? So we do the same thing. And here again, we're looking at the concentration of large particles. We've got a bed of small particles and large ones flowing over the top. Oh, sorry, other way around. Sorry, we've got a bed of large particles down here and small particles going over the top, the same as the video. And when we do these kinds of measurements, what we can see here is as the flow starts, we start to pick up, so that we have these large particles down the bottom, they start to get picked up and carried over the top. And then we get this flow of large particles slowly eroding into the material. And with this kind of information, we can really start to understand how does the system erode and how is that affecting the flowing behavior. We're kind of out of time, so I'll skip over the 3D stuff. But I just wanted to try to bring this back a little bit. I just wanted to give a shout out to SUCE. This is such an awesome image. It was very cool, very impressed. I'm so glad you guys are organizing these seminars. It's very nice to actually present what I do to you all, as opposed to just giving lectures on equations from 100 years ago. But I wanted to get back to actually how to surf a snow avalanche. And now that you guys understand a lot more about the physics and what's going on inside, and we have the segregation and mixing and crushing, I'll just give you a few little pointers for how to do it. The first step would be to not get crushed. That generally means being at the top. And to be at the top, you want to be very large. And the final piece of advice would be to never hit a tree. That's the #1 way to die in a snow avalanche. So just to sum up, we have these kind of simple models which help us to understand these materials. We can turn those simple models into more complicated models which start to represent the reality a bit better, but they come with a massive overhead of building complicated models. And then we can't get anywhere without benchmarking these ideas against reality. And so with our X-ray lab downstairs, we're able to measure all these things. We're able to measure the density everywhere. We're track any tracer particles if they're in there, measure the grain size, the alignment, the velocity fields, and the jiggling of these particles. And yeah, that's everything from me.
So I guess we should start the questions now. So if anyone has any questions, feel free to put them in the Zoom chat. The first question was, given how specific granular materials are, how did you become interested in this topic?
I don't know how specific granular materials are. We often make the quote that after water, they're the most commonly used materials on Earth. So I presented here about landslides and avalanches, but we do a heap of different stuff. So we work with coffee companies on the crushing, grinding, and extraction processes in making espresso coffee. We do a huge range of different stuff with mining industry, steel making, well, all kinds of different things. I think it's a pretty diverse topic, really. But how did I get stuck in it? So I did a combined science and engineering degree here. I did one of those summer scholarship positions just over the summer, and that was in this field. I just got hooked. Yeah, it was.
That makes sense. So what was the biggest challenge you faced in your career, and how did you overcome it?
So I have never worked in a real engineering company. It's just been universities the whole time. So I did my undergrad degree, then I did a PhD, and then I did a couple of research positions before starting here as a lecturer. And to move from being told what to do as a student to telling other people what to do, especially having PhD students, where you hire someone, you say for the next 4 years, you've got to work on this thing that I thought of. I found that very daunting. Becoming a manager, I guess, yeah.
Yeah, so there's a question in the chat said, regarding the ABS device, does it simply increase the chance of survival because it makes you all over larger?
Yeah, definitely. So one thing is it makes you larger, and the larger you are, the faster you'll come up. It also makes you, on average, less dense. And so the lighter you are, the faster you'll come up as well. Definitely.
Yeah. Okay. So what is the future of your studies, and where will you lead to next?
So we've had this X-ray lab for maybe 4 or 5 years now. And so we've been doing lots of exciting things here. So we have some new techniques now for tracking individual particles, but they can be used much more broadly than just tracking the little glass beads that I showed here. So we're using them for things like studying how, so if you look at your lungs, there's lots of, so they're not spherical particles, they're actually reasonably spherical holes. And your lungs have a dynamic motion as you breathe. And the changes in that motion very characteristic of a set of different diseases. And so we're really trying to use these techniques now to be able to understand new things in a whole range of fields. One of them around how these alveoli move inside lungs.
That's quite interesting. So do you have any advice for undergraduates trying to put themselves out there?
I would definitely talk to your lecturers about their research. Not a lot of us have an opportunity to talk about it in the things we teach. A lot of times the things we teach have very little to do with our expertise. Yeah, so if you're at all interested in research, definitely talk to people. A lot of us have research funds, so we apply for big grants and we've got money lying around to hire people to do stuff. So there's always the option of paid work there. And I'd say a very significant percentage of people who get started on research end up doing a PhD. It's a very addictive thing to do.
Okay. So how has working in engineering academia been, and what do you believe are the most essential qualifications or skills required for someone looking to go into academia?
Okay, so if you want to get started in research, something to keep in mind is that nothing that any of us do has anything to do with your undergraduate degree. So don't worry that you haven't taken a course or don't know anything. It is not relevant to the research typically anyway. So being interested and intelligent would be the two main ones. Yeah, I think the interest goes a long way, and dedication. And yeah, just finding out. It's quite hard to find out the research that's going on around you. I think if you guys can attend more seminars like this, hopefully you'll get so you'll hear from, was it 4 people this semester? Keep in mind there's about 40 academics, so there's plenty of stuff going on. Yeah.
What environmental engineering roles can you expect to be doing in the civil engineering, civil industry? And what would you call a typical day in one of these positions?
In environmental engineering?
Yeah.
So there's a bunch of different types of jobs that all call themselves environmental engineers. One of them would be doing remediation. So that could be people who go out, there's a contamination in the water or in the soil, and it needs to be fixed. And so they'll go in and they'll do the design work and then the construction work to actually fix that. There's a lot of other people who do sustainability stuff. So if you're applying for your 5-star, 6-star rating for a new building, they'll come in and they'll do the calculations there. There's a lot of other people doing master plans for cities and infrastructure to try to bring down the environmental cost. So a pretty broad topic in environmental engineering. Don't know if I could say exactly what people do all day. I'd say a lot of people, so if you're interested in going out and being on site, that'd be that first one where you're doing the actual remediation. That's where a lot of the site work happens.
So someone's asked a question in the chat. Did you go in university planning to do a PhD?
I don't think I knew what a PhD was when I started at uni. No, definitely not. But yeah, so I did the summer scholarship thing. I really enjoyed that. And I did my honors thesis with the same supervisor. Enjoyed that. And then I got a scholarship to stay on and do a PhD.
So just going off of that, what was your planned career path, and did you follow it as a student?
I don't think I ever had much of a plan. I don't know. Yeah. Yeah, so I definitely enjoyed so I did this combined degree with science, and I definitely enjoyed the science a lot more than engineering. So I did all the science subjects first, and then I had a year and a half of just engineering at the end. And then I did that research project, and so I just stayed in engineering. So most of the jobs I had between finishing a PhD and starting back here, they were mostly as a physicist, working in physics departments.
How do you know that you wanted to be part of the academic part of?
So academia's got a lot of bonuses. I get to do whatever the hell I want, which is quite nice. I get to teach whatever I want with some limits, and research really whatever I want, as long as it's academically justifiable. And so that's really nice. So yeah, all the things we've been doing with the X-ray lab and simulations and stuff. That's just ideas we had. It's been really nice being able to evolve them. It's something you don't get in any other kind of job, where you have no financial constraints and no need to ever actually make everything work. You can just keep trying. It's nice.
Yeah. So another question, how do you think COVID has impacted environmental engineering as a whole? And do you think the industry has adapted to this change?
I don't really know if I'm the right person to answer that, having never worked as an environmental engineer. I can tell you the people I know who are working have been, like, especially the people on site, have been on site the whole time. The construction's gone ahead. There's been pretty much no impact to them. I mean, a lot of businesses have been trimming back, except geotech. Geotech's been pretty good. They're still hiring. We've got so much tunneling work going on in Sydney. If you're looking for a job, geotech is always hires the best, and in my opinion is the most interesting.
So what's the next thing you're looking to research into?
So we've got this big focus on the X-ray lab and then developing new techniques there. Also kind of extending these simulations. So the ones I showed you, they're all a bit abstract still. So we've got plans to be able to actually use them to simulate a real situation. So we're working with a mining company at the moment on trying to simulate some of their equipment with these kinds of simulations. Yeah, I guess that's the kind of near-term stuff.
Yep. If there's any more questions in the chat, I think we'll wrap up now. But thank you so much for your presentation. I learned quite a lot and I quite enjoyed it. Yeah, so if you want, make sure to come to the next academic seminar on the 28th of April and check out the third industry workshop with ProBuild next Wednesday at 5 to 6. With that, I think the seminar is over unless you have anything to add, Benjy.
No, thanks for the opportunity to present to everyone. Yeah.
Thank you.
Cool, thanks.